Hello friends, we are discussing the chapter Laws of Motion, and in the last lecture we have discussed about the moment of force and moment of couple, that is torque, and in today's lecture we are going to discuss about equilibrium or the mechanical equilibrium and the center of mass. Now we are going to discuss the point mechanical equilibrium. Now when a particle when how can we know that a particle is in mechanical equilibrium? When the forces acting on the particle are zero. When the whatever forces which are acting on the particle, they are zero, the body or the particle is in mechanical equilibrium. But if there is a system of many particles, so now from one particle we have shifted to many particles. So if in a many particle system, how can a how can a system which is having many particles be in mechanical equilibrium? So if the forces acting on the system are zero, then the system or the many particle system is said to be in mechanical equilibrium. That is, the total force acting on the system of particles should be zero. Or we can explain in other words also that the velocity, or that is, if the velocity or the linear momentum of the system is constant or is zero, then the system is said to be in mechanical equilibrium. Also, in other words, it is that the acceleration, if the system does not have acceleration or the acceleration of the system is zero, then again the system is said to be in mechanical equilibrium. We conclude that whatever is the particle or the body or the system, if the total forces acting on the system or the body are zero, then the system or the body is in mechanical equilibrium. And also, of course, not only the system, but any small part or big part, any part of the system should follow this rule that the summation of all the forces acting on that part or the system, that should be equal to zero. Then the system is in mechanical equilibrium. So the next point which we are going to discuss is the stable equilibrium. Now here we are considering this convex part and there is a ball inside this part. So this ball is in equilibrium. Now if I try to disturb its position, if I move this ball from here to from this position to this position, and I again to this position or this position, and I again leave the ball, so what will happen? The ball will come from again here to here, it will move and then again it will come and stop at this position. So this position is a speciality that its potential energy is minimum. Now we know that potential energy depends upon height. So this ball is at the lowest height than any other height of the system. So this at this point the ball is at minimum potential energy and this ball is said to be in stable equilibrium. That is, even though it is disturbed, it comes to its original position within some time. So it is in stable equilibrium. Now the next case is unstable equilibrium. Now again here is the ball. The ball here is said to be in unstable equilibrium. Why? Because when I disturb the ball from its stable position, now it is here. So if I try to disturb the ball, then it will never try to come to its original position. It will try to go away. This is its position. just now. It is in equilibrium. It is at standstill at this position. But as I disturb it, as I move it from its position, then it will never try to come to its original position. It will go away from its original position. It will get disturbed. Why? Because this ball is at maximum potential energy position at this point. And when the ball is disturbed, it will try to attain a minimum potential energy position, which is a stable equilibrium position. So, this position of the ball is called as unstable equilibrium. Initially, the position of the ball is at its local maximum of potential energy. But when it gets disturbed, it tries to attain the minimum potential energy. Such an equilibrium is unstable equilibrium. So now we are going to discuss about the neutral equilibrium. So this is a plane and the ball is here. Now we know that the potential energy of this ball is constant over this whole plane and remains same at any position. So now if this ball is disturbed from its equilibrium position, it is moved on this side or this side, still because the ball is on the plane, the potential energy is going to remain constant according to the definition of potential energy, and hence the potential energy, since the potential energy would be remaining constant even after the ball is disturbed, the ball still remains in equilibrium at practically any position. So such equilibrium is called as neutral equilibrium. The next point which we are going to discuss is the center of mass. Now, what is the center of mass? It is the point at which the whole mass of the body is supposed to be concentrated so as to apply the Newton's laws of motion. Now, we know that the Newton's laws of motion are applicable to only point bodies, very small bodies. न्यूटनचे नियम फक्त ह्या पॉइंट बॉडीजसाठी आहेत. But in real life, are there such point bodies? No. In real life, the bodies are of varied sizes, various size and shapes. So how to apply these Newton's laws, which are for point masses, to the bodies having large masses? So the point at which we apply the Newton's laws, the point is the center of mass point of the body. At the center of mass point of the body, the Newton's laws are applicable. All the Newton's laws are applicable. The center of mass point helps us to consider these very, very big objects as point masses and apply point masses at particular location, and we can apply the Newton's laws of motion to that very big object. Now, we would be finding the center of mass. Now, if it is one particle system, the center of mass is the same. That is the position of the particle. But if the system has many particles, it is n particle system, then we would be finding the center of mass. Now, supposing this is the x-axis, this is the y-axis, and this is the z-axis. This is the origin, O. And there are some particles from M1, M2, M3, M4, up to Mn. So the system is n particle system. So this is M1, this is M2, M3, M4, M5, up to Mn. This is the last particle. And the first particle of mass M1 has coordinates x1, y1, z1. The second particle of mass M2 has coordinate x2, y2, z2. Similarly, x3, y3, z3. And similarly, for the last particle, the coordinates, the x, y, z coordinates are xn, yn, zn. Now here, or we can say this is the mass m1. The position vector of mass m1 is r1. The position vector of mass m2 is r2. The position vector of mass m3 is r3, r4, and r up to rn. So these are all the position vectors of all the particles which are inside the system of n particles. Now, so m1 up to mn are the total number of particles in the system, and r1, r2 up to rn are the position vectors from the center O, or the from the origin. So they are r1, r2 up to rn. Now, the position vector r of the center of mass. Now I want, this is the n particle system, and I want to find the center of mass of this n particle system. So what I'm going to do now, to find the position vector r of the center of mass, of this center of mass of this n particle system. Here it is, the position vector of center of mass particle is m1 r1 plus m2 r2 plus up to mn rn upon m1 plus m2 up to mn, which are the masses of the each particle. So now here, center of mass of this n particle system is, we, instead of writing in this laborious way, we do the summation. So summation, we write it in the summation form as I equal to 1 to n mi ri. So we can replace I by 1, 2, 3 up to mn, and we can write in this way, in this manner, in the full form. This upon, again we can, for m1, m2 up to mn, we will write I equal to 1 to n mi. So in this way, in short form, in the summation form, we can write the center of mass of the n particle system. But now we know that if the total mass, that is m1 plus m2 plus m3 up to mn, this will be equal to the total mass, each particle, masses of each particle. If we add it, then it will become the total mass of the system, so capital M. So instead of this, we can write capital M, which is the total mass of all the particles. So in this way, we find the center of mass of the n particle system. We have found that the position vector of the center of mass is summation of I equal to 1 to n mi ri upon summation of I equal to 1 to n mi. Now what is this r1? What is this r1? r1 is x1i plus y1j plus z1k. What is this r2? r2 is x2i plus y2j plus z2k. Similarly, for all we can write up to rn, we can write xni plus ynj plus znk. So this, each position vector of each particle, we are writing in terms of its coordinates, that coordinates of the x, y and the z coordinates. So this is the position vector of the center of mass. But if I want to write the x coordinate of the center of mass, the y coordinate of the center of mass and the z coordinate of center of mass separately, then what I have to do? That is, now we know that x1, x2, x3 up to xn are all the x coordinates of all the particles, having r1, r2, r3 up to rn as their position vector. If I want to find only the x coordinate of the center of mass, so these are all the x coordinates of the different points of the different particles of masses m1, m2 up to mn. So now here only the x, so I will write here x coordinate of center of mass, and I will rub here and I will write as xi. So the x coordinate of the center of mass point of the system is summation of I equal to 1 to n mi xi upon summation of I equal to 1 to n mi. So this is the x coordinate of center of mass. Similarly, if I want to find the y coordinate of the center of mass, now we know again y1, y2, y3, y4 dot dot up to yn are the y coordinates of the different particles m1, m2 dot dot up to mn. So here if I want to write the y coordinate, I write here y coordinate of center of mass, and here I rub this and I write y coordinate of the center of mass is summation of I equal to 1 to n mi yi upon summation of I equal to 1 to n mi. This is the y coordinate of center of mass. Similarly, if I want to find the z coordinate of the center of mass, then I will rub this and I will just write z, and here also I will write zi. So summation of I equal to 1 to n mi zi upon summation of I equal to 1 to n mi. So in this way we find the x, y and z, that is the x, y, z coordinates of the center of mass point. Now if this center of mass point is origin, so then r will be equal to 0 because it is center of mass point is origin. Center of mass is origin. Then center of mass is origin, r is equal to 0. So if r is equal to 0, this will be equal to 0. Then summation of I equal to 1 to n mi ri will be equal to 0 because summation of I equal to 1 to n mi is not 0. हे खालचं डिनॉमिनेटर 0 कधीच होऊ शकणार नाही, कारण ते मासेस आहेत प्रत्येका पार्टिकलचे आणि त्या सिस्टीमचं पूर्ण मास आहे. सो हे कधीच 0 होणार नाही, म्हणून हेच 0 होणार. सो आपण काय इन्फर करू शकतो? व्हॉट वी कॅन इन्फर इज व्हेन द सेंटर ऑफ मास इज द ओरिजिन, at that point the summation of I equal to 1 to n mi ri is 0. But what is mi ri? This summation of I equal to 1 to n mi ri is the moment of masses about the center of mass. So this is the moment of the masses about the center of mass. Now when the center of mass is origin, that is center of mass is 0, then the moment of the masses, center of mass is a point at which the summation of the moments of the masses of the system is 0. The next, this is a discrete body, that all the particles are separate. सगळे particles वेगवेगळे आहेत. But in our routine bodies, which we see, are the particles separate? No, they are continuous. The body is continuous. If the body is continuous mass distribution, continuous mass distribution with uniform density, that is the density of all the body, density everywhere is uniform, then how are we going to write the center of mass of such continuous body having uniform density? For here, so for R, the center of mass, because now there are no separate प्रत्येक वेगळे particles नहीं आहेत, they are all continuous. So we are using the mathematics, that is the integration from the mathematics, and we will write here this is equal to integral of R dm upon integral of dm. But now we know that integral of dm is addition of all the masses of the bodies. So this integral of dm will become m, that is the mass of the body. So we can write integral of r dm upon m. So in this way we write the center of mass of a continuous body having uniform density. If I want to write the x, y and the z coordinates of the center of mass of a continuous body like this with uniform density, then I will replace this r by x. This is equal to integral of x dm upon m. So the integral of x dm upon m, this is the x coordinate of the center of mass. Similarly, the y coordinate of center of mass is integral of y dm upon m. Similarly, the z coordinate of the center of mass is integral of z dm upon m. So in this way, we write the x, y, z coordinates of the center of mass of a continuous body having uniform density. So we have completed the center of mass, and in the table in the book are given coordinates of center of mass of uniform symmetric objects. Thank you.